So 7.4 has a bunch of stuff in it that didn't really deserve its own section. So they just made a section out of some miscellaneous facts that you can do with radicals. So the first thing is a thing called combining like radicals, which is exactly what it sounds like it would be. You're familiar with combining like terms. These are like terms because they have the same variable. If you combine them, you just look at the coefficients and you do the adding rules. A positive 4, a positive 3, you combine those, you get a positive 7, and you just leave the x alone. We've done that a million times. Like radicals just mean they have the same radicand. So these are like radicals because they both have the same 3 radicand. So the answer has the same 3 radicand. You combine these by just doing the adding rules. So positive 2, adding a positive 4, so that's a positive 6 root 3. These, at first glance, are not like radicals because they have different radicands right now, but that's fixable. What we're going to do is rely on our lesson about simplifying to do that. So if you have that squares, cubes chart that we've made a few times, 25 is a perfect square that goes into 50 twice. So we can rearrange this that it has a 2 underneath. The square root of 25 is 5. It could bump into this other 5, which would multiply and get us up to 25. For 18, 9 is on the squares list. 9 goes into this twice, so this can also have a 2 underneath, and we've created like radicals now. The square root of 9 is 3, which pops out. 3 bumps into 6 to make an 18. And then those can put together. A 25 plus an 18 is 43 of those root 2s. One more, basically the same style. The 12 and the 75 are unlike right now, so we have to look at simplifying. For 12, 4 goes in 3 times, so 3 can go under. Square root of 4 is 2, which multiplies the existing coefficient up to 8. For 75, 25 goes in 3 times, so 3 is again underneath, and we have our like radicals, so the answer has that same radical. The root of 25 is 5 times the existing coefficient would be up to 30, and we're going to again add the coefficients up to 38, and that's what combining like radicals is about. One small addition, if there were exponents or something involved, like if this had an x cubed, and this had an x cubed, we simplified those by dividing the index, which are these invisible 2's, index into exponent. 2 into 3 goes once, so an x could come out, and a remainder of 1 leaves an x in. Same thing over here would happen. 2 into 3 goes once, so an x comes out. Remainder is x, so x stays in. If you have something like that, these are still like. 25x can still add 18x to make 43x, and the 2x can just stay underneath. Just make sure your radical sign is long enough always to include everything that's under it. You don't want to make it look like something's out when it's actually in. The second skill of the day is multiplying radicals. So what they're going to be looking for you to do is either do some distributing or some FOILing today, depending on the problem. But there's an underlying helpful skill in this, a little shortcut to show you. So some people, if you gave them root 7 times root 7, would at first think to make that root 49, which isn't a bad thought. It's not the best thought, but it's not a bad thought. Root 7 times root 7 is true, root 49. But a better answer than the root of 49 would be to go to a regular 7. And if you see that happen once or twice, you might recognize if you take a root times itself, you're always going to get the radicand just without the root sign on it. Like root 6 times root 6 is going to be 6. If you want to work through root 36 to get to 6, that's not wrong, but that's a little bit unnecessary. If you had to do a root of 143 times a root of 143, I don't think you want to work through the root of some big giant number just to get right back to regular old 143. I think you're better to just absorb that detail of any radical, any square root, times itself is going to make the radicand just without a root sign. So we'll be able to use that once or twice in the remaining bits of the lesson. For a problem like this though, we're just looking to distribute. So this is a cube root times cube roots and cube roots. We're going to get a couple cube roots. If I do the cube root of y times the cube root of y squared, remember we add powers when we multiply, we'd be up to 3, because that has a 1, add powers up to 3. If this tries to multiply this, if a 4 multiplies a y, the best we could do for now is just put 4y. Sometimes that's all you can do. Sometimes you want to try to make something better, and in this case we can make it better. If the index is at least equal to the exponent, or if the exponent's bigger, look to divide it. 3 goes into 3 once, evenly, so the cube root of y cubed can just be a single y that's coming out. If I had something here like a 4, I'd have also left some variables in, but that didn't happen. This, we're just stuck. We can square root 4, but we can't cube root 4, so this is just stuck with cube root of 4y. This is a foiling problem. We've got 2 things times 2 things. We need to get 4 things out of it. So if we multiply the firsts, we're going to get a root 10 plus the outsides get us a root 14. The insides get us a root 15. And then the lasts give us a root 21. We should always look to see if there's any numbers here that could help us from our squares list. But like 4 doesn't go into that, 9 won't do any of that, 16 won't do any of that. All the other squares are bigger than those. This is the best we could do. But if we had something like a root 12 or a root 20, some of those, we can simplify some of those, but that didn't happen on this one. Here we have some coefficients in front, so ruling on that is the coefficients want to multiply the other coefficients. The roots want to multiply the other roots. We'll keep those separated. If you don't see a coefficient, there is a 1 there. If you want to write 1s in, you can feel free to do that. But if we multiply these, we get a 2 root 18. If we multiply these, that is a 4 root 21. If we multiply these, that's a 3 root 30. Because again, what I'm doing, the numbers in front, the coefficients multiply to stay in front. The radicands multiply to make a new radicand. And then when we do these, 3 times 2 is 6, and the roots would be a root 35. As always, we should try to think if we can simplify any of this. If 4 doesn't go into any of those numbers. 9 doesn't go into these, but 9 does go into that twice. So I'm going to leave a 2 under there. The square root of 9 is 6. Times the coefficient that's already waiting would get us up to a 6. So 2 under, square root of 9 is 3. 3 times that gets us up to 6. Think about our other squares. 16 can't go into any of those. 25 can't go into any of those. So the answer would be those 3 standing pat, but that first one we could make better, so we did. The final skill of the day is called rationalizing the denominator. The rule on this is you're not allowed to have radical signs on the bottom. And the way we're going to fix this, we're going to multiply the top, and while we're at it, multiply the bottom by the same number, top and bottom, to make the root go away. And we're going to use the trick we just did a few minutes ago with radicals. So if I want square root of 5 to not be a square rooty number, but to go away and be a normal, good old-fashioned rational number, I could multiply the bottom by root 5. Because on the bottom, if I take root 5 times root 5, that's going to make a normal old 5. If you want to work through in your mind that being root 25, to get to 5, you can do that, but I think you're wasting some time. Okay? Just remember, anytime a square root multiplies itself, you're going to get the radicand just without the square root sign. So bottom multiplies root 5, that means the top has to multiply root 5. On the top, these are different kinds of numbers. The best you can do there is to have 7 root 5, and that's called a rationalized denominator. We don't have a root on the bottom anymore. For this one, we don't want to have root 3 on the bottom, so we multiply by root 3. And if we're going to multiply the bottom by root 3, we'll multiply the top by root 3. On the bottom, root 3 times root 3 is good old-fashioned kindergarten 3. On the top, we get the 6 times the root of 3. A second ago, with that problem, we were done. This problem, we're going to upgrade one more step, because regular old 6 can divide regular old 3 to get a regular old 2, and the square root of 3 is still going to hang around. the question is written this way, remember, that means the same as a root 5 on top and a root 7 on the bottom. When they write this, it means this. There is a root on the bottom, and we're not going to do that anymore. So to fix that, multiply the bottom by root 7, so the bottom is a normal 7. Multiply the top by root 7. Roots times roots make roots, but now it's 35 for multiplying the radicanes. Don't try to divide these. This is a rooting number, this is a non-rooting number. Those can't interact with each other in multiply or divide world. Think about root 35 if we can simplify that at all, but like 4, 9, 16, all those common numbers from this, the squares list, 5 to 25, 6, and 36. None of those squares go into 35, so that's as good as we're going to be. If they start to, well, let's do cube roots. Cube roots, we shift our attention now to cubes. But we're not going to multiply by the same number. With cube roots, you have to be a little bit more clever. Okay, 9, if you multiply 9 by 9, you'd get a cube root of 81. 81 is not on that list. That does not help us. So what we want to multiply here by is a cube root on the top, a cube root on the bottom, to generate a number that's on the list. If we can make one of these numbers on the bottom, we're going to be able to do that root. 9 can't be turned into 8. 9 can turn into 27 if you multiply 3. So on top, we'll multiply by 3. On the top, we get the cube root of 15. On the bottom, cube root of 9 times cube root of 3 is going to make the cube root of 27 we targeted. And the cube root of 27 is 3. And that's our best answer available. It's tempting to divide these, but you're not allowed to. Root numbers can't divide non-rooted numbers. If it's under the radical, it can't be messed with. This, we're back to square roots, so we're back to what we did over there. If it's a square root, just focus on the bottom and multiply by the exact thing. This has a root of 5b, so multiply by that. The top has to multiply by the same thing as the bottom. So on bottom, a root 5b and a root 5b is going to be a regular old 5b. Top, we're going to get a root. 2 times 5 is 10. And the a and the b just join forces. And for like third or fourth problem in a row, don't try to divide these. Radicals can't divide non-radicals. You're just stuck with that looking that way. The very last part of the homework still has roots on the bottom, but they're going to start to have adding or subtracting. So it's important for you to know something, be reminded of something that you do know, is the entire tops and the entire bottoms have parentheses around them. They're there, they exist, it's a thing. For this, sometimes people are tempted to multiply by the exact match, and that isn't going to exactly work in this process, but it's close. Okay, but a second ago, if we had a root, we just multiplied that same root, we got a regular old thing. However, if you try to have an adding or subtracting combo, multiply foiling with itself, these would make a normal 5, which is good. These would make a normal 3, which is good. But these would make root 15s, and these would make more root 15s. And now we got a bunch of root 15s on the bottom. And you created a problem while solving another problem. If we foiled this right now, root 5s would disappear and root 3s would disappear, but we'd create root 15s, so that isn't going to work. For us to get this fixed and not create those other root 15s, what we're going to do is take the problem that we had with the minus and just switch the sign. Whatever this had, switch the sign of it, do the same thing on the top and bottom both with the sign switch compared to how we came in. And when you foil this, this would be a negative root 15, and this would be a positive root 15, and that doesn't exist. Those would wipe each other out. So answer for this, 1 times anything is that same anything. On the bottom, these multiplied would make a 5. These multiplied would make a 3, but it would be negative because they're different. And then negative root 15 and the positive root 15 would wipe each other out. 5 minus 3, that's a 2, and that's the best answer we could get from that. There's a name for this. This is called the conjugate. Conjugate is just a fancy math word that means take what you had, switch the sign. So this, again, will multiply by the conjugate. Focus on the bottom, 2 plus root 5, and I'm going to use a 2 minus root 5. If I multiply these on the bottom, I'm going to get a nice whole number kind of answer. I'm going to do the same exact thing on the top. Whatever I do on the bottom, I'm doing on the top. Top I would want to distribute, so 3 times 2 is 6, minus 3 times root 5 is just 3 root 5. On the bottom, 2 times 2 is 4. This would be a positive mass. This would be the same negative mass. So this and this wipe out. You don't need to worry about that. Positive times negative is negative. A root 5 times a root 5 is a basic old 5. And I shouldn't have drawn a box around this answer as soon as I did. Because if I do this math, that's going to be a negative 1. We don't really want to leave 1s on the bottom, even if they're negative 1s. What we're able to do is divide negative 1 into both numbers on top. Negative 1 into 6 would make that a negative. Negative 1 into negative 3 makes that a positive. That doesn't need to be a fraction anymore. That's now our best answer. Last one of these, again, you always focus on the bottoms. Root 5s, root 7s. If this had a minus, we do a plus. We're doing the conjugate. On the top, we're doing that same root 5, root 7 with plus that we did on the bottom. On the bottom, root 5 times root 5 is basic 5. Root 7 times root 7 is basic 7. That's going to be negative because they were different. So negative 2 on the bottom. And then for the top, this is actually a problem that I did 5 minutes ago. When we started to just FOIL, we had this exact problem on the top. We made it root 10 plus root 14 plus root 15 plus root 21. If we FOIL out the top, we've been there, done that a few minutes ago. That's the same FOILing that we just did. So you're going to do that kind of FOILing again. And that's a wrap. The 7-4 homework is monstrously long in the book, and then I help you guys out. So the homework goes to 88. But what I've always done on this page when we're working to 88, we do the 3s. So 3, 6, 9, 12. Sometimes we skip the 3s. Today we're going to do the 3s. So 3, 6, 9, 12 up to 87. We're going to do the 3s on that page, 308 up to 87 would be the final one that you have to do because that's the final one of the 3s. And that's it.